Thank you, and thanks for inviting me. It's really been a great seminar series. Like I said, I can't really watch it live because it's 6 a.m., but I definitely try to check out the recordings. They've been really good. Yeah, like I'm going to be talking about first principle calculations of light ion reactions, and this is work that is done mainly here in Livermore, this beautiful campus that you can see here. But before, wait, okay, but before talking about reactions per se, I'm going to give a little bit of background about what the nuclear data and theory group does and how first principle or ab initio nuclear theory fits in. So the goal of the nuclear data and theory group is to model nuclear phenomena and combine this modeling with experimental data in order to produce accurate data evaluations that can then go on and be used in nuclear data libraries, codes for transport, et cetera, et cetera. There are many regions in the chart. I'm not going to go over what modeling types happen here, but I'm going to focus on what this talk is about, which is ab initio nuclear reaction theory in this case, which mainly focuses on lighter systems. So everything I'm going to talk about is going to be for maybe is applicable for up to mass 16. And the problem after that is it just becomes too computationally expensive to actually do nuclear reaction calculations from first principles, but I'm going to get a little bit more into that. So in ab initio nuclear reaction theory, you model the reaction of, in what I'm going to talk about today, binary systems based on their constituent particles. So the fundamental degree of freedom is a nucleon. As an example here is the DT fusion, where both the deuteron is described as having a proton and a neutron. The triton is described as having proton and two neutrons. They all come together, they fuse, and then helium-4 and a neutron comes out. So at every step of this reaction, we are still describing it from the fundamental constituents. And this is why this process, solving this problem grows exponentially in difficulty as you go to heavier and heavier masses. So this is something that we really are looking forward to solving, but it's a little bit difficult. And why would you need to do it in the first place, right? Why would you want to model a reaction in such a manner? As an example, I'm showing here the Big Bang nucleosynthesis network, so or part of the Big Bang nucleosynthesis network, I should say. So from about 3 minutes all the way to 20 minutes after the Big Bang, nuclei fuse together in order to produce elements up to mass 7. And if you look closer at the abundances of these elements, then you start figuring out that things are not lining up perfectly. So what is plotted here is the abundance of lithium-7. These are theoretical calculations. So what the expected abundance of lithium-7 is based on what the baryonic density is. Now, WMAP measured this baryonic density, or measured is a good word, and they found the value here. We believe we have an astrophysics measurement for the lithium abundance, that is this band here. And you will notice that the theory prediction does not pass the point of the two measurements meeting. So this is a tension between theory and experiment. And there are multiple reasons why this could be. It could be astrophysics reasons. It could be the measurements are not what we think they are, but there's also the more elephant in the room reason, but that perhaps we don't know the reaction rates in this network as well as we think we do. Therefore, we are ending up with wrong abundance predictions. So this, you might think, okay, this is not the case. We know them very well. But then you find out that when people redo experiments or try to measure quantities, you get discrepancies. And in this case, you get pretty big discrepancies. So this is 7 beryllium NP. For example, it's this leg in the reaction. This is important actually in this problem because it depletes beryllium-7. And the lithium-7 that we observe today comes from beryllium-7 that beta decays. So that survive the Big Bang and then beta decays. So a higher 7 beryllium NP means you deplete more 7 beryllium, therefore you increase the final lithium abundance. However, this discrepancy here was not even close to being enough to solve this problem. I should state this, but still it is an issue, right? How do you have two experiments, both of which have very small error bars, and they differ in this case by what, 40% or something like that at very low energies. So this is where theory comes in. If you have a theory that comes completely from first principles, you're not fitting to the experiment you're trying to describe, then you can actually make a bona fide prediction and say, hey, you know what, one of these two experiments is so much in tension with the theory that, you know, they might have some systematic error. But in order to do this, not only you need to have a good predictive theory, but you need to be able to actually assess the uncertainties that come with your prediction. In fact, I'm going to talk about our steps towards arriving to a prediction of this reaction, but not this reaction just yet, just this one, the 3-helium-NP, a bit later on. Okay, we're not only interested in making very, very precise measurements to discern experiments, but we're also interested in other astrophysical reaction rates, such as reaction rates that come into the helium burning reactions. So two alpha particles fusing together to form beryllium-8, then capture another alpha, make carbon-12, capture another alpha, make oxygen-16. And we're interested in the ratio of the reaction rates of these reactions in order to be able to say something about how much 12 carbon versus 16 oxygen exists in the universe. And again, ab initio reaction theory has a place here, because if you look at, for example, helium-4 and carbon-12 fusion, you see that data stops at some energy. And that's a little bit obvious to this point, right? You have Coulomb repulsion. After a point you can't really measure. You've been measuring for years and years and years. And to make matters worse, you see that the error bars in the experimental data points are becoming bigger and bigger. So from a theorist point of view, it is questionable what the use is of having a point that has such a large error bar if you're going to be fitting the S factor to it. It doesn't contain a lot of information. It will come with a very big denominator in the chi-square for the fit and so on. However, if you have a predictive theory, such as an ab initio theory that you know can describe the data here, you can trust it to extrapolate all the way to low energies without having any particular issue. So again, this is the place where ab initio reaction theory fits in. What we would ideally want is to have a calculation that can take us all the way down to the astrophysically relevant energy here, where, you know, realistically you cannot expect an experiment to measure at any near term. Finally, because ab initio nuclear theory treats the fundamental particle as being the nucleon, so the proton and neutron, one can study the emergence of phenomena that happen when you are near the threshold of where continuum states begin and where bound states are. So one of such examples is nuclear clustering, which is my favorite emergent phenomenon. So clustering refers to the formation of substructures inside the nucleus. So I'm showing, for example, 6 lithium clusters into an alpha particle and a deuteron, beryllium-8 into 2 alpha particles, carbon-12 into 3 alpha particles, and so on and so forth. These are all states that will affect the spectrum if exist and are expected to find near thresholds. So to sort of put it more into a picture, this is the Aikida diagram. You have, let's say, 20 neon. You have excitation energy going up. You reach the alpha decay threshold, and that is where you expect to find states that look like 16 oxygen plus an alpha particle. You go up to the next threshold, the 2 alpha threshold, you expect to find states that are like 12 carbon plus 2 alphas, now, this is not the whole story, though. Ideally, you expect these states, right, to really affect the alpha reaction rates, because you expect these states to have high alpha spectroscopic factors. So with high alpha spectroscopic factors come high alpha widths. And then if you have a big alpha width, you know that state will saturate the alpha strength. So it will essentially collect all the alpha strength in itself. And therefore, it will be a major player if you're trying to accurately compute what an alpha reaction rate is. But that's not the whole story, like I said. So we do see other broad states that are higher up in the spectrum not really close to a threshold, that also have a rather large alpha decay width. And this is challenging from a theoretical perspective. Like, how can a state actually maintain its cluster characteristics so further up from the threshold? Like these are states that are about what, 5 MeV from the threshold, but still it maintains a nice alpha plus something structure. So that is how this phenomenon arises from the many body complexity is really something that I find intriguing, at least. Okay. So if we want to compute reactions from nucleons, we need obviously to be able to describe the asymptotic parts of the reaction where the two nuclei are very far apart. The only thing that you care there is about the internal dynamics of the nuclei. So we treat the internal dynamics of the nuclei using the no-core shell model. This is basically harmonic oscillator expansion for a many-body system. We make a harmonic trap, throw all the nucleons in. It makes the lowest Pauli allowed state. And then slowly we start allowing more and more excitations as in order to get a better description of the ground state of the system. So the more excitations you allow, the better description you get. Problem is, the more excitations you allow, the more difficult the problem becomes. So solving for the ground state of the nucleus in this case amounts to diagonalizing a large matrix. And the more excitation, the bigger the matrix. However, this is not the way to do reactions, right? Because you need to have some way of breaking apart the wave function into the two fragments that you want. And this, okay, moves, wait, there I am. So we also need to be able to have dynamical descriptions of the nucleus, where the nucleus has fragmented into these two or more reacting nuclei. So a target and a projectile in some definite relative motion so that we can keep track of what's going on. Putting everything together, the total wave function of the no-core shell model with continuum can be written like this. It contains these relative motion states where the two fragments are in some definite relative motion, but it also contains states that look like no-core shell model states, but for the aggregate system now. And the purpose of these states is to go beyond the resonating group method type states like these, so that we can describe swelling of the nuclei, some particle exchange, how they deform, perhaps when they come together. And once you write down your wave function like this, when you make this assumption about it, all you are left with is trying to figure out what these unknown amplitudes are, these CL and UN. In matrix form, the equations look a little bit like this. So you have sectors that deal with either the NCSM part of the wave function, so this aggregate system, or the RGM part of the wave function, where you have definite relative motion. It's a generalized equation because the RGM channels are non-orthogonal, right? You can pick a set of asymptotic quantum numbers. It doesn't mean it's orthogonal to another asymptotic set of quantum numbers. So that's pretty, yeah. And we solve this using the microscopic R matrix method. So what this essentially boils down to is the internal wave function of the fragments will be a shell model type wave function. It will be a harmonic oscillator type wave function. However, the relative motion of the fragments will be in whatever state it needs to be. It could be in a scattering state, it could be in a resonance state, or it could be in a bound state. It doesn't matter. It's still solved with a microscopic R matrix. At this point, I should say that you can also do microscopic R matrix in the function space. You don't have to do it only in the real R space where you separate the two nuclei. And we sort of use a mix of these two based on which thing we're trying to compute. But yes, this is basically how we get everything. So does it work? The answer is yes. Otherwise, I wouldn't have made this lengthy introduction. So you have, I'm showing here protons scattering off of alpha particles. These are differential cross-section. We observe a generally good agreement with the data, and the same for deuterons scattering off of alpha particles. We, again, have generally good agreement with the data. I should say that in this case, right, I should emphasize, there is no optical potential and there is nothing fitted to these specific systems, these lithium 5 or this lithium 6. these come completely from the nucleon-nucleon and 3-nucleon interaction. However, what we can see is that there are small discrepancies. For example, here, you see the line overshoots the data a little bit. Here, the dip doesn't go as much as the actual data points. So these are uncertain. We would like to know if these are uncertainties in the theory, if there is a problem with the interaction that you are using. So you know exactly what's going on. I will talk about uncertainty quantification in a bit. But before I do that, I should focus on, okay, that's something I carefully neglected to say. What is the interaction that we actually use for this entire thing? There's no optical potential here, right? There is only an interaction between 2 nucleons or 3 nucleons together. And for this, we use chiral effective field theory. It's essentially a bag of goodies. It provides us a direct link with the underlying theory, which is in this case is QCD. It comes as a systematic expansion, which also means that it comes with, hopefully, quantifiable uncertainties. So hopefully at each order in this expansion, we obtain a better description of the nuclear interaction. So, and in a systematic way, we also know what the error we are making because we are truncating the rest of the series is. So if we can quantify that, we can include it in the theoretical prediction. Also, this means that, well, what is also good about chiral effective field theory is that there is a relatively small amount of parameters that one needs to fit in order to have the full interaction. I say relatively small because I come from a background in nuclear structure, where in shell model, you might have to fit, 80 parameters, and okay, fine, it's a big fit, but it's still doable. Here, we're talking about like 20, 40, these types of parameters. So it's generally doable. It's not a huge amount of parameters like you might have to do in the nuclear shell model, the traditional shell model. The final good thing is that 3-nucleon forces also appear organically. Their parameters are also constrained by nuclear observables, so they're not fitted to every system that we have in order to reproduce something. So that's also an added bonus. And for the first thing I want to talk about today is how do we actually fit these 3-nucleon interactions, and how does this affect our reaction observables? And what's the uncertainty actually that comes with it? So first things first, to know what we're talking about, there's 2 terms at the third order, that 3-nucleon interaction. One comes with a low energy constant CD, so a parameter that needs to be fit. It's the 1-pion exchange. And the 3-nucleon contact term comes with a low energy constant CE, which is another parameter that we need to fit. Traditionally, the way we fit this is you take the Triton half-life, you take the Triton binding energy, and you have 2 constraints, you have 2 parameters, you fit those to them. But when you do that, what you're ignoring essentially is the inherent uncertainty in your theory. So you're making the actual prediction of the theory pass through those data points, but you're completely ignoring the fact that your theory has an error bar. There is no reason to expect it to reproduce the Triton binding energy and half-life to the 5th decimal at the first place, if it means that your constraint is actually ruining your description of other observables. To put this more into a picture, I'm showing here the expectation value for the Triton half-life over the theoretical over the experimental, and this with varying CD. So these are different theoretical calculations for different CD. The thin blue line is the experimental error in the Triton half-life. So ideally, if we only use the experimental error, we would find out where our lines cross this blue line, and where it crosses the edges, that would be our uncertainty in our determination of CD. However, this red box and this green box are the theoretical uncertainties. Is what happens if we take into account our theoretical uncertainties. So you see that these dominate, and they give you a much broader range of CD and CE. What this translates to is having a modified chi-square, where you actually have the uncertainty of the theory added in the denominator. So essentially, it becomes more diffuse, so it avoids overfitting. So okay, let's say we do this. We now have an expanded range for CD and correspondingly CE. Still, doing a calculation with for ab initio theory, let's say for a neutron scattering off of an alpha particle, is not computationally very easy. It does take some time, and it takes enough time where it begins to be a little bit of a time sink for no reason. So for this, we develop emulators for the computer codes. And for the emulators, we use Gaussian processes. The emulator's job is to be basically an interpolator. So you do a few of your calculations, you construct a Gaussian process model taking into account the input, those calculations as input, and then you can essentially query what the output of your code would have been had you made a calculation with a new value. To make this a little bit more pictorial, I have here, let's say, a model that has an output X and an input X and an output Y. Let's say the dashed line is what you know what the exact model would be, but then you only have 3 predictions. So there's 3 data points. A Gaussian process would give you a mean that passes through these data points in this case, and an uncertainty for all the places where you do not have data points. Because you have an uncertainty, you know which is the next point you want to sample in order to reduce the uncertainty. So here we have only 3 data points. We add 2 more. You see that the uncertainty is constrained in the interior region. You add 2 more. You have essentially reproduced the model in a completely no assumptions way, right? You did not make any assumption that this was a straight line. This was simply a Gaussian process model. Although you see that if you try to use it for extrapolation, it fails miserably. But that is not something we are looking to do. Okay, so wow, this one shifted a little bit. So we did this for a neutron scattering on alpha particles. We take this CDC plane, we scatter some calculations around it, and then we try to introduce extra constraints on the fitting in order to see how it reduces the uncertainty in our prediction of neutron plus alpha scattering cross-section calculations. So first we introduced the helium-4 binding energy. So whereas your prior would have been this full square essentially, now you just have this posterior here. Still, it comes with a pretty large uncertainty. We introduced the charge radius of helium-4. It doesn't do much to reduce the uncertainty. But finally, obviously, if you include the resonance positions, then you really constrain your calculation. You now have very good agreement with NDEF and the experiment, and the posterior now has become squished. It's still pretty decent in size, given that we're fitting the resonances, but it's definitely much better than this. However, like I said, this is computationally expensive. So what I showed before had about 80 calculations in it. And neutron scattering on alpha, sure, it's computationally difficult, but it's not the end of the world. We have calculations, though, that take days, and it's not realistically feasible to do high fidelity calculations for those 80 points, for example. So what we are trying to do now is look into mixed fidelity modeling, where one does a high fidelity or does a few high fidelity calculations, but then can fill in the gaps in this prior space with low fidelity calculations and see if this can help us decrease the deviation, how the emulator predicts our computer model. So we do this using PP co-kriging, and this is the work of Kevin Quinlan from LNL, who we're collaborating with. And we see that really the number of, as you increase the number of high fidelity samples, of course, you get lower and lower average root mean square deviation, but then co-kriging shows a 50% reduction at very small numbers of high fidelity samples, which is the domain that we really want to work in. So we want to do 3 high fidelity calculations, very difficult, very precise, and then we just want to flood it with low fidelity samples. And we see that PP co-kriging really shines in this area. We can also go a step further and see how new low energy constants and terms can actually affect our cross sections. What I'm showing here, just beforehand, is the 3-helium NP reaction that I promised. I am missing the data from CarbRune, which is very nice high precision data, and that is definitely my omission. I need to fix this. I didn't have time. So here we did a 4-dimensional we altered 4 parameters where the CD and C are the same as before, the 1 pion exchange in the contact term. But now we added a subleading contact term that looks like this. And it has essentially 2 more parameters, E7 and E8. And this will become a little bit more important in the next slide. But you see that this multiplies an isospin dot product. So in general, we find that you see that most of these realizations of 3 nucleon force do not reproduce the data. So this either points to a problem in the 2 nucleon sector, or it means that the order at which we have the chiral interaction is not sufficient. This is the type of term that we need, all right? Because this is the type of term that takes us all the way up here, where the experimental data are. Now, I should say that this is not a full calculation, might need to include the DD channel as well as a virtual excitation to shift this resonance to the correct position. However, what we can do is something else. We can look at the sensitivity of this cross section on all the low energy constants we are varying. And when we do this, we see that with increasing energy, there are different low energy constants that play a role in describing the cross section. So it's not simply, a flat thing where, CD affects the cross section this much, CD affects the cross section this much. It actually varies with energy. And in fact, you see that here, the E7 and E8 terms start playing a major role. And this is because this resonance here has an isospin counterpart. So this is an isospin 0 resonance, but there is the isospin 1 resonance very close to it. So because this term carries this tau1 to tau2 term, the position of the resonance exactly seems to be controlled by this term as well. So it's actually very, how should I say? It's very encouraging that we see that what we know from physics to be reflected in the sensitivity index. Oops, I went the wrong way. Okay, finally, just talking about precision, there are other reactions in solar, what do you say? In the sun, where we really need precision. And this, for example, is the 7 beryllium P gamma radiative capture reaction. So we have been able recently to compute this capture reaction with 3 nucleon forces. And we are now in the process of trying to quantify the uncertainty of this calculation, not to the big extent that I just showed with the various 3 nucleon force calculations, but just more realistically, the chiral uncertainty and so on. But you see again the same problem, right? The experimental data stop here, and this is exactly where you need theory. And again, if you try to just fit to data, you might run into issues where one data set has more points than the other, one is more precise than the other. So you need to be able to know how to calibrate them and so on. So this is a pure result that doesn't really take into account all of these problems. Okay, how much time do I have left? Oh, cool. Okay, I spoke earlier for alpha burning reactions. So to get back to this, can ab initio theory describe alpha burning reactions? The answer is yes. So this has already been done back in 2015 from Sir Daryl Hathisari. So they showed that they get relatively good agreement for phase shifts up to N2LO with lattice methods. We recently managed to update our code base in a way that allows us to do alpha-induced reactions, and we find a similar good agreement with the data. What is shown here is actually the effect of how you regulate the 3 nucleon force on observables. And what we found is that using only a local 3 nucleon force regulator is actually working against you. So by local here, I mean it only depends on exchange momentum, right? So you see that if you use a local interaction, which is this dashed line, a local regulator, which is this dashed line, you move further away from the experimental data. Whereas if you use a local, non-local regulator, you are staying in the same ballpark. In fact, if you look at the differential cross sections, you can see that you are agreeing very well with the differential cross section, only with the local, non-local, not so much with the local. But that's not all our new formalism allows us to do. We can now do reactions with p-shell projectiles. So what we decided to explore here was the structure and reaction, or a continuum of beryllium-12. So on the left, showing the spectrum of beryllium-12 if you include different types of clusterizations. So first, you have only 6 helium plus 6 helium clusterizations, and you get a decent spectrum. Here you have 4 helium plus 8 helium clusterizations, and you have another type of spectrum with different types of states. If you combine them together, you get this, let's say, alpha spectrum. But then if you include the 11 beryllium plus neutron, you get a whole wealth of states, right? Now, there is actually a couple of things to note here. One, you will see, for example, in the transfer reaction that most states stay the same. So this is 6 helium, alpha, 8 helium, right? The red line is without including the neutron decay channels. The black line is with including the neutron decay channel. And what is a little bit surprising here is that you see a big shift when you include the neutron decay channels. So you have an effect where the neutron continuum is actually affecting your cluster states. So it's affecting the reaction rate or the reaction widths that come into play in the clustered reaction. So this was a little bit surprising, at least to me, but it's kind of cool if you think about it. Sorry. Furthermore, we also predicted the 0- state below threshold. It was actually observed this March for the first time. It's a little bit above threshold in the observation, but still, this was pretty exciting, to be honest. Okay, I have time, right? Yeah, cool. Sorry. So, given that this is a national lab, and I mentioned before that what we're trying to do is provide accurate data evaluations, it stands to reason that one of the things that we are trying to do is relevant to nuclear data. And nuclear data has many uses apart from astrophysics. I think there was one of these seminars before that talked about reactors. There is medical imaging, border security, stockpile shearship, reactor construction and design, and so on. So we want to see if ab initio theory can actually help in these endeavors at all. So, okay. Okay, this slide looks weird. I don't know why, but anyway. What is here is actually two standards. On the left is a kilogram. So it's nice, it's being kept in vacuum. It's no longer a standard, but that's a different discussion. You try to keep it pristine, and you know that it always has the same weight, right? And when you want to measure the weight of something else, you measure it against this guy, so then you know how much the actual weight is. On the other hand, neutron cross-section standards are working standards, unlike the kilogram. So neutron cross-section standards are continuously assessed, updated, and improved. What this means is that, for example, the 6 lithium NT, which is a cross-section standard, is always assessed and improved given that new experimental data might come into play. So again, this is a cross-section standard, which means that if you want to measure a neutron cross-section, you can measure it against this 6 lithium NT cross-section, and then you can obtain your final cross-section by taking the ratio. However, it's only a standard up to 1 MeV. And if you see the spread of experimental data down here, you can see that why it's only a standard up to 1 MeV. It becomes difficult to make an accurate evaluation here. And this is where ab initio theory can help, right? I mean, we don't have a problem of fitting to data. We can always make a prediction and it will be what it is. It's there as long as we include all the relevant channels. In fact, what we're trying to do now is, well, we have done, I should say, is, let's say a neutron comes and impinges on lithium-6. You have many different types of outputs. And what the new formalism really allowed us to do is, by being faster in calculating, it allowed us to include all of these channels simultaneously in the calculation, which is what is necessary in order to push the cross-section standard further. So we can take the NCSMC model. We can tune a little things because we really want to reproduce experiment to the very precise level. So we need to tune, for example, the thresholds so that they are correct to the KeV level. And we have to tune the resonance so that they fall exactly where they should. And we reproduce the cross-section for the NT reaction pretty exactly. However, we're not after the NT reaction cross-section. What we're after is the angular distribution, because these are more difficult to measure. And this is actually what is needed by our experimental counterparts in order to simulate their experimental apparatus, I should say. So without any further adjustments, we were able to get angular momentum distributions that are pretty decent, I should say. We're actually pretty good, in pretty good agreement with experimental data. And in some cases, we're actually doing better than NDEF, which is pretty surprising. Well, I shouldn't say surprising, but anyway. So to conclude, because I think I'm close to time, we have made quite a few first steps here. We are definitely well into looking into uncertainty quantification for our calculations. It's really important when you try to compare to experimental data to really have a handle of how well do you know what you think you know. And we see this very abundantly, especially if you remember at 3 helium NP plot where you can fluctuate wildly. Moving further, we have been able to describe alpha clustering fairly nice, at least in the 2-alpha system. We are confident that this will continue. This description of alpha clustering can and will continue to bigger and heavier systems. So this is something that we're looking forward to. And finally, we are now at the point where we can actually start mixing experimental data with the ab initio calculations in order to be able to not only arrive at predictions on by themselves, but correct any possible issues that might exist within nuclear force.